Hello, welcome to this session. Today I will introduce our team's work, the design and implementation of device Keepalive state, which can be used for implementing local line migration and VMM fast restart with pass-through device support. We will first give an overview of the design and then dive into some major details. First, let's have a recap of the problem. System update is the pain point of cloud vendors because system update is usually taking too long time. So we see more service downtime for customers. The existing solutions can be divided into several categories. First choice is to move the VMs somewhere else to allow the system can be updated. The typical solution of this category is line migration. However, line migration doesn't support pass-through device very well. The other choice is to keep the VM at local. Then an option is to live patching the kernel. It is good for small fixes. However, big kernel changes will raise the failure rate. Our focus is the final category. Update the relevant components separately or in a whole on local system. Examples of this category include the proposal from Oracle to do the Qemu Live update. Alibaba also had a paper which talks about updating the KVM module. Looking into the solutions, two questions need to be answered. First, do we allow pausing VM? And second, do we allow to reboot the host? If we allow pausing the VM, then pass-through devices and kernel update can be supported naturally, because pass-through devices can be suspended within the VM and then resumed when VM restart. If we don't allow pausing the VM, which means we can't require VM cooperation, then we will have two further choices. First, don't allow host reboot. Then we can't update kernel. We can only update userland VMM, typically Qemu. Here we still need to pass the state of the pass-through device to the resumed Qemu. We also need to pass the guest memory mapping across the restart. Steve from Oracle also had a proposal for this case. VMM fast restart wants to solve the final category, in which we don't allow pausing VM and we allow host reboot. This is the most flexible solution, which means kernel and Qemu can both be updated. Here we can leverage Kexec-Reboot to boost the reboot time. We also want to support pass-through devices. There is a special situation here. During the reboot time window, the pass-through device has no owner. Since we can't rely on the guest driver to suspend the device, so the choice we have is to keep the device alive across the reboot. So here comes our proposal and implementation. We introduce a device Keepalive state for pass-through devices. We will talk about the overall idea of the proposal and then dive into some major details. As shown in top right corner of the slide, we introduce a flag in the core device data structure to denote a device is in the Keepalive state. What does it mean by putting a device into Keepalive state? It means the device hardware is still alive, although it has no owner. It may continue to issue DMA and IRQ. However, the host software must not notify the hardware state of the device. It can't bind the device to any other drivers either. And on the other hand, the device software state, which is managed by drivers, must be saved at one of two stages if it can't be restored without clobbering hardware, either at the time the device enters Keepalive state or at the time the host reboot. It depends on whether it is affected by Qemu runtime operation or not, or it is configured or maintained by the kernel or not. The whole Kexec-Reboot procedure consists of two incremental stages. Stage 1 is related to Qemu. When Qemu starts, it opens the pass-through device. When Qemu quits, it closes the device. This will cause the device to be enabled and disabled, thus changing its hardware state. So if we want to keep the device alive across the restart, we need to set it into keep alive state before Qemu quits. This is called stage 1 keep alive state. Stage 2 is related to kernel reboot. Some devices, such as IOMMU, its driver maintains its own state as long as the kernel is running. But when kernel is about to Kexec-Reboot, the state will need to be preserved so that it can be handed over to the new kernel. This is stage 2 keep alive state. Here we can see that stage 1 keep alive states can be used for implementing Qemu Live update. This is an alternative solution to the FD passing over EXEC. It also can be applied for implementing local live migration. This slide shows the example Qemu commands for implementing the VMM fast restart. We put the guest memory in a DEX device, which is a DRAM emulated persistent memory, and turn on its share property. In this way, Qemu can pick up the guest memory from the persistent memory after Kexec-Reboot. The Qemu command migrate set capability X ignore shared makes the save VM command ignore the guest memory region that has turned on share property. So we don't need to copy the guest memory into the snapshot. The Qemu command set keep alive is a newly added command to set all the pass-through devices into keep alive state. It also specifies a UUID token. When Qemu restarts after Kexec-Reboot, it needs to specify this token to the VFIO device parameter so that the kernel can verify the resumed Qemu has the permission to own the pass-through device. After the resumed Qemu load the snapshot, we issue the set keep alive off command to clear the keep alive flag for all the pass-through devices. After that, the pass-through devices will start working as usual. So as shown in this picture, a lot of data structures or software states are evolved in the lifetime of the VM. To implement VMM fast restart, we need to figure out which ones need to be preserved and which ones we can recreate across the Kexec-Reboot. There are some rationales to help determine this. First, does it need to be saved at all? If the state are pure software state, which means it doesn't depend on hardware state, or it can be restored by reading back the hardware registers, then we don't need to save it. If we can only restore it by clobbering the hardware register, then we will need to save it. All the gray states in the picture are those we don't need to save because we can reconstruct them without clobbering hardware registers. And second, we don't want the resulting state saving code to be too much intrusive to other kernel components. Pass-through devices are managed by VFIO driver. It is reasonable to put major device keep alive management logic in VFIO layer, so as not to touch other components too much. And third, if we need to save it, which stage does it belong to? Is it manipulated by Qemu runtime operations, or will it only be destroyed by kernel reboot? For example, The VFIO PCI device data structure has hardware-dependent states. The underlying PCI device will be disabled when Qemu quits, and it will be enabled by Qemu restart. So it belongs to stage 1. In later slides, we will look into these Keepalive states in more details. Now let's dive a little bit deeper to see how we keep alive the two major device Keepalive states, IRQ and DMA. The challenge for keeping IRQ alive is that during the Kexec-Reboot, both hardware and software are not available to handle the IRQ. CPU is undergoing reboot and reinitialization. Software is not ready either. There are two options to keep IRQ alive. First one is to mask IRQ when the device is put into Keepalive state and unmask it when VM resumes. In this way, device can hold from issuing IRQ during the restart period. The problem of this approach is that MSI masking is an optional feature of PCI devices, which means there are some devices that don't support MSI masking. Another approach is to leverage posted interrupt, which we choose here. It doesn't depend on MSI or MSIX, so it is more generic and has more coverage. The IRQ setup and teardown are triggered from the VFIO PCI device layer. It goes through the PCI and IRQ core layer down to the IRQ remapping driver to allocate or free the IRTE, which means interrupt remapping table entry. Meanwhile, the KVM side will allocate posted interrupt descriptor, PID, for the vCPU. It will be connected to the specific device interrupt vector via the IRTE. So here we basically have three things to preserve: PID, IRTE, and the device interrupt vector index. The device interrupt vector index is not shown in this picture. It is saved in the Qemu snapshot. Next, we will talk about how we save PID and IRTE. There are also two options to notify KVM side to preserve PID. One is to introduce I/O control comments so that Qemu can issue to KVM side to save the PID. Another one is to leverage IRQ bypass mechanism, which is currently used by VFIO driver to notify KVM side to enable or disable posted interrupt mode. We introduced two callback interfaces for the IRQ bypass consumer data structure. When the device enters Keepalive state, the callback save consumer will be invoked from the VFIO side. It will eventually trigger a newly added callback in the KVM x86 ops, which will save PID and set the suppress notification bit in the PID. And for IRTE, again, two options for preserving it. It is a long code path, as we mentioned, to set up or tear down an IRQ. It starts from VFIO driver, goes through the PCI core and the IRQ core layers, and finally it arrives at IRQ remapping driver. If we want to make the PCI core and IRQ core layer to be aware of the Keepalive saving and restoring, then we will need to introduce APIs and pretty much code changes into these two core kernel layers, which may be much intrusive to the two layers. So we choose another approach by which we reuse most of the IRQ setup and teardown code paths. We just check the device Keepalive flag at the IRQ remapping driver. If the device is kept alive, then we don't free the IRTE when IRQ is torn down. Instead, we save the IRTE aside. We also record the mapping between the IRTE and the IRQ vector index within the device so that they can be reconnected when the device IRQ vector index is reset up. In this way, we can introduce less intrusive code change for all the involved layers. For DMA states preserving, we need to preserve the DMA page table, domain ID, and the various IOMMU configurations. For example, the root table of the IOMMU, the context table, etc. There is a dilemma situation for us about whether to preserve IOMMU domain or not. The IOMMU domain data structure is a software data structure which can be recreated without clobbering hardware state. If we do recreate it, we will have pretty much code change to IOMMU driver. On the other hand, if we preserve it, most of the code change will be in VFIO. Then, do we want to consider other device pass-through framework, such as VDPA? It looks more reasonable to let the IOMMU driver to do more things than both VDPA and the VFIO duplicate the efforts. Currently, our POC work chooses to preserve the IOMMU, and this leaves this issue as an open. Device ownership authentication is a security issue we need to consider. This is because when the pass-through device is put into Keepalive state, it will be detached from its owner. When the resumed VM is trying to reattach to the device, there must be a mechanism to verify the ownership. We leverage the VF token mechanism, which is an existing feature of current VFIO driver, to do the job. A token will be set into the VFIO device when it is put into Keepalive state. Then, when the Qemu restarts, it needs to pass the token to the kernel VFIO driver in order to reopen the pass-through device. Kexec-Reboot procedure also needs some modifications. We introduce a Keepalive callback notifier before Kexec-Reboot happens, where the stage 2 Keepalive states can be preserved, and all the Keepalive states can be copied to the persistent memory to pass to the new kernel. After the new kernel starts to boot, all the Keepalive states will be copied back from the persistent memory so that device states can be restored. Pass-through device list is another important information that needs to pass to the new kernel so that the new kernel can identify the Keepalive devices and do special handling during PCI enumeration. We also need a memory handover mechanism to pass all this data from old kernel to new kernel. Anthony from Oracle has a proposal for this. For Keepalive devices, PCI enumeration procedure needs special handling. Basically, we can't reinitialize the device. Instead, we need to restore the states from the data passed from old kernel. Meanwhile, we can't reassign PCI bar resources to the Keepalive devices. Instead, we need to inherit the resources from old kernel, which are already recorded in the bar registers of the devices. So until now, we have talked about how we handle the many issues we will encounter for the VMM fast restart. However, we still have many opens. First, we still can't make the Keepalive flag transparent to PCI core code. We check device Keepalive flag in MSI, MSIX, IRQ setup and tear down code paths to avoid clobbering hardware MSI, MSIX registers. Do we want to check the Keepalive flag in all PCI core code paths, since we already introduced this flag? would that be too intrusive to PCI core code? And what about PCI enumeration failure because of resource conflict? How do we notify Qemu about this? And since all the dependent devices along the I/O path also need to be kept alive, how do we handle the states of these devices? For example, switch port and root port. They may register IRQs for different PCIe capabilities. Can we just disable them when Keepalive operation starts and read events back from their status registers after reboot and re-inject those events into guest? And what about SRIOV and SIOV support? PF device states also need to be preserved. How do we do that? Currently, we have finished the POC of Qemu fast restart and the full VMM fast restart. With our testing environment, which is Haswell and Broadwell platform with Intel NIC card, YouTube video streaming and SCP workloads in VM can be restored after Kexec-Reboot. We hope this effort can go to upstream. So we'd like to have your comments and suggestions, and cooperation is welcome. Thanks, everyone. Any question?